So it's now my pleasure to get to kick off our morning session. We are assembled. I want to thank everybody for all of their attention yesterday, and I think we're going to have some more fun, and I want to start off with some critical questions in mitochondrial transplantation. Let's see. So our topics for today that I hope to do in about the next 30 minutes, and I'm going to try to leave a little bit of time for questions and answers, which means that I have to be done in about 30 minutes, so we have some remaining time, is that I want to talk about some of the new science from our laboratory. I want to be able to just at least acknowledge all the gaps that we've been talking about and talk about one in particular. I want to talk about dosage a little bit that is bothering me. And then I want to turn our attention a little bit from science, from content, to the politics of science, and to the structure of science, and to how we might improve that structure. And then I want to at least share my opinions, and it's just purely my opinions, on what I think our greatest opportunities would be in the near future. So now just a little bit about me. Not everyone here knows me, and so a few things that I started out my academic career in Chicago at the University of Chicago.
Thank you.
And then I spent 10 years at the University of Pennsylvania, where I had the chance to work with Dr. Wallace in his laboratory. And for the last approximately 10 years, I've been at Northwell Health as the chair of emergency medicine and an investigator in the Feinstein Institutes for medical research. And just a really quick thing, I know many of you don't know much about Northwell Health, and so I'm going to unabashedly just tell you it's an organization worth paying attention to. Probably the fastest growing health system in the country, the fastest rising medical school in the country, now in the top tier, approximately $25 billion, 90,000 employees, does about 1% of the healthcare in the United States. And that platform is important because it's also leading in innovation. And an example is this conference. I could not have done this conference without the innovative leadership that is stressed from Northwell Health to allow me the luxury of putting this on. Now, my intellectual curiosity is also another sojourn, which is I started in ischemia and reperfusion, and cardiac arrest was the disease that I took on. And quite honestly, you have to own your biases. I have a bias, which is that typically when we pronounce people dead, I don't actually think they're really dead. So that's a bias that I have to own, and it's one that causes me both continuous ability to push myself to do more things, but to question what we do and to come up with better and newer therapies, which is what we do at Northwell. And that journey led me to the basic science of resuscitation that I have the opportunity to lead nationally, where ischemia and reperfusion, so ischemia, being without oxygen, is such a common factor in so many different diseases, both of emergency medicine and that afflict people all around the world, and I know we can do better with that disease, and I now see mitochondrial transplantation as being a major part of that. Now, a bit about our lab, and I want to tell you a bit about sort of what our concept map was, okay? And in a really simple way, one of the things that I learned was that with cardiac arrest, it turns out that a major problem is mitochondrial dysfunction. Now, that was not known 25 years ago. It is now well accepted. And so, with the realization that mitochondria are in some way moving about in the body, that opened up this field of mitochondrial transplantation, which is a new concept, which is, can we use the migration of mitochondria therapeutically to do a transplantation and improve human health. And of course, the sort of my summary for those people who are kind of new to the field is that mitochondria are a little bit like emergency doctors, okay? We do not stay in our lane, okay? We go everywhere where we're needed, and I think that's what mitochondria do. And this was a slide that one of my colleagues helped when I told him that this is what I wanted to talk about. And I showed it at the American Heart Association, and just a week ago, this was the headline off of one of the medical things that appears on the internet, which is that cells are swapping their mitochondria. Look at those little mitochondria on cars right there, okay? And we had that image a year before they did that. Okay, so some of our recent work is what I want to highlight here. And I want to move right into some science. And the first question that we took on is, could mitochondrial transplantation improve outcomes after cardiac arrest? And I want to highlight Dr. Kei Hayashida, who's sitting somewhere, hiding probably, well, he's in the back. There he is back there. Yeah, he's hiding. He won't even put his hand up, okay? Very amazing, amazing colleague, okay? And he was really the person who had this idea. And I just want to go public that this was not my idea to do. I actually thought it was foolish. And Kay convinced me otherwise, and here's part of how he did that. Is we did a study, and in our laboratory we have an amazing cardiac arrest model, and that model is one that does a really severe thing to an animal, which is that we put rats into cardiac arrest for 12 minutes. That's the longest period of time without blood flow of any laboratory in the world in terms of working on cardiac arrest. And that's important because it gets you to the severity that we experience as people, okay? And then what we do is we come along in our laboratory and we actually do CPR on those animals and we resuscitate those animals. Now, while that's going on for this experiment, we then prepared mitochondria for donation. And we used Jim McCulley's method to isolate those mitochondria. It came from the muscle of a littermate animal, and those mitochondria were prepared, and we would administer those mitochondria after we would do CPR on the animals. And we have three groups that I'd like to show you the results of here. And one group got full-on mitochondria. Another group, very important, got frozen, thawed, disrupted membrane, all messed up mitochondria. And then another group got vehicle. And what you can see that I'll show you in just a minute is the outcomes. And for this, we have a 72-hour model that we recover these animals for 3 days. We evaluate all kinds of things in them. And I will refer you to the papers if you want to look at those. And here's sort of the money on this, all right? And what you can see here is that whereas 55% survival with bad neurologic outcome, we had almost 91% survival in this group. We published this, but we asked a few more questions because the next thing we said was, I don't know if you can see this graph up here, but look at where they die. They don't die like immediately. They die a little bit later. Anybody want to guess what they die from? Maybe brain injury, okay? So how do their brains look? So this was another sub-study that we did off of this, and this is laser speckled flowgraphy. And what you can see up here, I don't know if this is going to work. Wait, this is 2 hours after the cardiac arrest, and you can see there was all this nice circulation in the brain, and 2 hours afterwards, the circulation is not nearly so good. And when you give disrupted mitochondria, very similar, but when you give full strength mitochondria, what you can see is look at all this nice flow that has returned here. And if you read our paper, we quantify that. And so this was our publication from 2023. And lo and behold, a week after we published this, Scientific American did a full page on that paper. And I encourage you all to take a look at that paper. You can read the details importance of it. Now, I want to go to a few other questions that I think are equally exciting, which is, gosh, if this is working, like where in the bloodstream are these mitochondria going? Because we're just injecting these mitochondria into the femoral vein of these animals. And so this is unpublished data that I want to share with you. Where do these mitochondria go? And to do this study, again, we're going to look in a rodent model, and we have two groups of animals. One is just completely normal animals. And we compare that to animals after they've gone through a cardiac arrest. And what we've done here is we've labeled our mitochondria with a fluorescent dye and given good mitochondria to both of the groups. And we also give vehicle to both of the groups. And what you can see is, and then we use a technique called flow cytometry of the blood components. And I'm only going to show one little component of this fairly large study. But I want to show you the macrophages that are floating around in the bloodstream of these animals. And I want you to pay attention to both what's happening and the timing. So here's sort of the money shot on this. And what you can see in this group, this is the group that gets mitochondria after cardiac arrest. And this group is almost 55% labeled with mitochondria that have been taken up by those cells. That's a huge amount of all of the macrophages in that animal's body is now labeled with fresh mitochondria. But what's so interesting is in a normal animal, it's a very small amount. So that's the first insight that I want to share, which is that when we talk about where mitochondria go, it becomes context dependent. It is different after ischemia than in a normal animal. So, and we have to learn why is that different, and I don't know right now. But the second thing is I snuck something in here. You'll notice there's no label on this axis. And that's because this is not minutes down here. This axis is in seconds. And so what you can see is that the greatest uptake is already perhaps by 30 seconds, which is so early that we just didn't even plan for a result like this. And what you can see here is, look, this is a minute and 15 seconds after we inject them. We've already lost the peak of this. They're already starting to disappear. Very important kinetics in this study, and we are now trying to understand this more fully. Now, and so I just want to say that the answer, if somebody asks you, hey, where do those mitochondria go? The answer is it depends. It depends on the conditions. But maybe it's really, really fast, and maybe much faster than we ever anticipated. Now, some additional unpublished data is that we then also did a similar breakdown to just say what organs are these mitochondria ending up in? Where did it, like after this cardiac arrest, where did they end up? And again, we use this sort of model with both normal animals and then cardiac arrest animals, and then we check the organs for this signal at various times. And I'm only going to show you brain. And the story is different in different organs, but look at what happens in the brain here for a moment. With a normal animal, you inject them, there's almost no uptake in the brain an hour afterwards. In a cardiac arrest animal, huge uptake in the brain after an hour. So very important data that really, at this point, we have no full explanation for. What a great area for our young people to continue to look at. And so my conclusion here is there's no brain uptake in normal animals, but there is significant uptake after ischemia. And the kinetics on this, unlike what I showed you before, is delayed in terms of getting to the brain. So there's a pathway there that is still hidden to us. Now, I want to turn to another important topic, which is hemorrhage, shock, and bleeding, the injuries that we see on the battlefield and in sometimes domestically as well. And I want to highlight again my team that asked the question, can mitochondrial transplantation improve outcome after lethal hemorrhage? And the model that we hear, I know we've got a few surgeons in the room, and this is a model that they call bad shock, okay? Because this is an animal that's, you bring the blood, you suck blood out, the blood pressure goes down to 30. Trust me, if your blood pressures were 30, you would be very, very unhappy, okay? And we leave those animals there for 90 minutes, and just so, no, that's a model that kills 75% of the animals, okay? And then we try to resuscitate them, okay? And what we do is we resuscitate them with giving them twice the volume of their whatever blood we took off. We give them 2.5 times that amount. It's very standard. And then we look at what is their outcome. And we found something that was really surprising here, which is that just as we thought terrible outcome with traditional resuscitation, and just so people know, this is like what we do to patients right now. We give them LR, okay? And you can see that with mitochondria added to that, 75% alive, and we are now continuing to do that. We're so sort of shocked by that one that we actually took a pause and we're redoing the whole thing because we want to be absolutely sure before we report it we've got everything right on this, because it is a radically different approach, and there is almost no resuscitation technique in the world that would have this kind of effect on hemorrhagic shock. So what do we know? Really quick, because I want to wrap on our science, and I encourage you to look at both our studies, and we have about 6 abstracts here. So just some things that we know. We know that mitochondrial appears to be beneficial, at least in animal models, for both survival and neurologic recovery. We now see this. I haven't shown you the data. We have this data in 3 species, okay? Rats, mice, and pigs. We know that there's something very rapid about the uptake of these mitochondria. We know that there's something also very preferential, that mitochondria get into damaged tissues differently than normal tissues. There's similar trends in hemorrhagic shock. We have wound healing. We have a CHF model that is amazing as well. We've got studies that are now beginning to come out in stroke, toxicology, Alzheimer's, and aging. And in conjunction with Mitrex and many other people, we're now convinced that as much as I love quickly grinding up mitochondria to inject it into an animal, I don't think that's going to be a sustainable model for the emergency department. I don't think that's a sustainable model. We've got to come together and figure out a way that we can have some banked mitochondria that are available to us relatively easy. And so we are now deep working with Nick Myrna, who's here somewhere from the engineering school at Hofstra. We're thinking about how can we create a bioreactor, an incubator, that can kind of like automatically take some cells, grind them up, stimulate them, collect the mitochondria, so that we could have a good source of mitochondria that would be easy for us to use. And so those are some of the things that we're working on. And for those of you who want to read papers and citations, yes, we have papers and citations. So if you want to follow some of our literature, these are the papers that we put out just in the last couple of years on this. And there are 6 abstracts back here from our young people that tell you all our cutting edge stuff. So now I want to change focus a little bit and go to what are our barriers. And from my perspective, and I'm going to move through this reasonably quickly because we have a lot of barriers, but I see most of them as being things that we could really surmount. So 2 buckets of barriers. The first is the scientific gaps in our knowledge. These are like the things that we don't know. And we are going to have to learn this stuff. Stuff like, and people have talked about it already very well. Like, what is the right source? What is the best isolation technique that we can use? How do we maintain these mitochondria when we go to give them to a patient? How do we deliver them to tissues? What about safety and immunity, and many, many more? And the other bucket, I'm going to say, are our structural barriers that we're also talking about at this meeting. And those are things, those are the politics of science. Those are things like poor collaboration, things like the politics and seeking profit over some other endpoints, and academic ivory towers that sometimes lose track of why they exist. Fragmentation in laboratories and duplication and funding and alignment and many more. And for the first bucket, you know, we're just going to have to do more research to overcome that. And in the second bucket, I do think we could have some better and more innovative structures. And so I want to think about both of these buckets for a moment. And so turning to the first bucket, I want to just take a smack at what we all do. And this is a critique that is as focused at me, at our own laboratory, as any other place. I'm really worried about dose, okay? And we know that there's some ways that we can describe dosing. And part of it is, when I read through the literature, we don't do a very good job of describing our dose. Not yet, not full enough for me. And like, there's all these different ways. We can weigh it, we can count the particles, we give the volume, we give a size distribution. And remember, a lot of these particles, they're not all the same size, folks. And so if I gave you a mixture of tennis balls and bowling balls, and I told you that I was going to tell you how many particles were there, you would say, whoa. Also, purity, we don't yet, like, what is it 90% pure or 95% pure? These are things that we could work out in the next, like, we could work some of this out in the next 12 months if we work collaboratively together. Then there's the functional parameters like ATP generation, O2 consumption, state 3/4, which is what a lot of us love, ROS generation. But now when we get into transplant, do we need another function? The ability to enter new cells, right? The ability to remain in new cells, permanence and durability. We're going to have to work some of this out and define our dosages, and ultimately we'll probably end up with some function over mass ratio where you pick one of these and you put it over one of those. But this is something that we could make some real progress on in the next year, and I hope we will. Now, why is the standard dose so important? Well, first of all, if we're going to treat patients and animals, we need to get standardized dosing so we can compare our studies. But it's also, we can compare our studies from one to the next. And even within our own laboratories, an important question is, are we being consistent from 1 week to the next week? Something that we really worry about. And just my editorial comment is, when you don't have dose defined for your therapy, so you say, oh, I've got this new therapy, I can't quite tell you the dosage, all right? First, you're at the very beginning of a field, so that's really exciting. That's great, okay? But second, you've got to use extreme caution. Extreme caution. And you can never say that you've got an optimal dose, because if you can't define the dose, you can't have an optimal dose. So this reminds me a little of Hamilton, okay? I'm not throwing away my shot of mitochondria, okay? We got to be careful, but we have the opportunity to move quick on this. In this room, there would be the ability to knock this out and have a consensus paper in short order, and I hope that we will do that. So a few other barriers that I want to now turn to, structural barriers and some of the politics of science that we could maybe make some progress on. And I want to talk just quickly about structure and function. And my God, folks, we are mitochondriacs in this room. Okay? There's no organelle that has a more interesting structure that must therefore dictate its function than a mitochondria. So I think we can do better in our structure of how we do science. That structure will dictate elements of function, and conversely, when you want a new function, so if you want science to go faster, we want a new structure. We can't expect it to go faster if we just keep using our same structures. So I did what any logical person would do when they really don't know anything about a subject, which is I went to ChatGPT. And I said, what can we do to innovate a better structure? And my question, how can we accelerate the rate of science progress? Okay? And I just put that into ChatGPT. You're all welcome to do it. I did a bunch of varieties of it. And the first thing it did is it gave like 3 pages on how to do it. And it says, well, one thing you got to do is you got to reform your funding incentive. Does that ring true? Yeah, like we got to reform that. Well, we can maybe add some AI. We can do open science. We can streamline our workflows and interdisciplinary high-risk support. So all of these are like there's literature on this out there. So then I asked the AI. I said, well, give me some examples of this, okay? And it came up with, well, you could become a focused research organization. I said, I've never heard of a focused research organization, so I read a little bit about it. And lo and behold, it's a new type of organization that is needed to accelerate scientific progress. And I'll let you all sort of pull that up. It's a fun little website that went to. It sort of has a viewpoint. Here's sort of your big companies. Here's your startups. Here's your academia. And right in the middle is a focused research organization that can maybe take the best of several of those kind of organizations. Then it gave me another example. It said, well, here, go to Accelerate Science. Now, I was like, silly me. Here, I've been trying to accelerate science, and I just could have, like, gone to Accelerate Science. Now, this is like by Seed AI. It just went live in February of 25. So this is a month out, okay? You can join this organization. There's a few little organizations in this. Meta, Amazon. There's a few organizations that are thinking about how we could accelerate science, okay? So we need a new concept for an organization, and what I want to suggest is if we're serious about it, what we want to do is sort of form an exploratory group of this body that would begin to think about it and maybe come back with something. It needs to be a little bit like academic, it needs to be a little like a company, it needs to be patient focused, but it needs to have the strengths of those and not the limitations. So I encourage all of you to think, and that's what we'll be talking about in the final session. What would this new organization look like? Like, if I give you a blank piece of paper and say, draw your organization that we should create together. I want to see a lot of drawings, and I'm sure there will be a lot of drawings if we do that. And I hope that that's what we will do for our final session here. Now, you know, I gotta say a few words on funding. None of these things are gonna happen if we don't get funding, but I want to say something else. But like a startup, like this is not a field that it takes a huge amount to get going because we're so close to the beginning of this field. And that's an advantage. This is relatively cheap. If you were gonna transform cancer care, like don't even think about that unless you've got a couple billion with B ready to go, okay? This is not that kind of a field. This could be transformed with M's, with a few millions. And I don't think we should be afraid of it. We are at the very beginning, but we gotta have some funding. Now, I'm gonna wrap up sort of my thoughts here with immediate opportunities and next steps. Things that we could do right now grab a hold of, and if we come back together, if people want to come back together, we could report on some of those. So I think we should plan to meet in about a year, okay? I don't know if people agree, but for the final session, we're going to want to hear your opinion on that. I think we need a writing group that will begin to knock out some of the low-hanging fruit on some of the consensus work. And I see John Brestoff in the back. And so, John, teeing you up, right? Yeah, I know. And he's running to the back, as he should. As any academic who says, wait, I still want to have a career, Lance. You know what I mean? So, but we've got a great opportunity. We can do some knowledge gap documents to NIH and other funding sources. I think we should start an ad hoc exploratory think tank to really think through what is the kind of organization that would serve us, that would serve all of us, not just the academics, not just the companies, not just the families, that would serve all of us. What would be that kind of organization? And to be honest, I don't know, I don't have the answer right now. And we need some seed funding. So in summary, what I've tried to do for the last 30 minutes here is sort of introduce you to some science, things we're doing in our lab, from cardiac arrest to hemorrhagic shock. Tell you my big concern, we gotta take care of some of these gaps. I'm really worried about dosage. We got structure and function things to work out, and I think there are some immediate opportunities that will predictably accelerate our science, and we should have short and long-term strategies on those. So I want to prep you now for the final, sort of concludes my part of the talk. I do want to prep you for what we'll be talking about just after lunch as we all come together. And I want everyone to participate as we think about, should we have another meeting? Who is going to help put it together? Should we form a new organization or a mitochondrial transplantation society? Can we do some consensus work to better define some of these areas? Can we develop a clinical trials network that is robust, ready to roll, so that as we do things, we can roll those right out? Can industry help drive some of this faster towards implementation and science? What is the best role for our families, our patients, and our foundations? What is the thing that we can all do together that will help this field? And how do we align all the interests to garner more collective funding that will push the field forward? And finally, how do we get the message out to the public? And how do we develop an improvement in public trust that we heard last night and throughout these discussions that has eroded so much? So finally, I just want to thank Northwell Health. This conference would not have happened without the support from Northwell Health, just as it would not have happened without all of your support. Also to emergency medicine that sees the mitochondria as, you know, it's just, I gotta tell you, emergency medicine doesn't have like an organ. Like, you know, Giuseppe's got his organ, he's got the kidney, but emergency medicine, because it deals with oxygen, it's got an organelle. And you know what that organelle is, okay? The mitochondria is the organelle of emergency medicine. And to my mentors, to Doug Wallace, to this is Nick Lane, who have really inspired me over so long, I say thank you. And of course, I could not present anything were it not for the incredibly hard work of my inspiring laboratory. And I have the best deal in the world because they think I'm teaching them. Yeah, they don't, please don't let them know. Like, they teach me every day. So I want to thank all of them and thank all of you for paying attention to me. And there's some time for questions, so thank you.
I'll go ahead and take the patient question first. All right, so something I haven't heard about at this conference yet is overdosing.
Does anyone have data on what organ would be most susceptible to overdosing if we were to do like a, rather than like a specific organ, like a full body transplantation? So what organ would be the first to fail, and or what are the highest concerns for overdosing?
So I'll give you my quick one. So there's two things that we kind of worry about, I think. One is that actually in the injection, you would do damage. For example, if you have too many particles, they might start to act as, they might stick together and plug up arteries and things like that. And we have worried about that when we do an injection. So that is always an issue. In terms of actually amping it all the way up, I don't think there's much data on that. There are some studies that have shown some toxicity when you give too much. Okay. Another, please.
Great talk, and only a couple of issues we have to worry about in there. Thank you.
That's right.
On the dosage, you following up on that. So from yesterday, I didn't ask the question, and so I'm sorry. I want to ask it of you. When you compare the amount of a transfusion, of a transplantation, into whatever the body, it just doesn't seem like there's enough there to really push things too far along. So if you could help us all and maybe speculate a little, because I know you don't have all the science that you need, but speculate a little, what do you think might be going on there?
Well, thank you for that question. And I'm going to speculate, and I'm going to hope that I'm not thrown out of the scientific community for my speculation on this. I'm going to give you what I actually think is probably likely. So what Dr. Mortensen is saying is, like, it seems like we don't give enough of this to account for the effect that we're seeing. Is everybody? And Martin Picard yesterday talked about signaling. So what that makes me think is that if what we're not doing is actually like taking a mitochondria, getting it inside a cell, and then that mitochondria saves the cell, I think something else is going on. And so if I had to speculate, I would say that I learned from Dr. Wallace that mitochondria are electromagnetic quantum devices. And what I actually think the mitochondria are doing, and the mechanism that's not there, is I believe that mitochondria are shooting photons out. That is, they are producing light. They are sending photons out, and I believe those photons are being captured by other mitochondria. Those photons are being captured by antennae, by cellular particles that then vibrate like an antenna would do when they hear that message, and will change the signaling inside the cell. And what that would imply, and the reason that I cannot go public with that, is that means that there is a hidden communication system within all of us that we're using all the time to create messages and to drive signaling and to change biologic behavior that's not chemical. Oh my gosh, this is a really good way to get thrown out of a medical society, okay? So you asked me the question, you asked me to speculate on it, and if there are people who want to help understand what is potentially one of the most fundamental communication systems going on inside our body, I believe it's going to turn out to be light, photons, energy. And it's completely invisible to us right now. Can you imagine? What an opportunity. If I was a young person doing a PhD, there could never be a better thing to take on. And if I was a company that was going to put some bets down on the board, you want to go to Vegas on something? Man, oh man, would I be willing to put some bets down on a field that's so fundamental to all of biology that nobody yet has the first therapy for.
So just to follow up on the dosing question, for what it's worth, these are mouse experiments, but it's an ongoing series of experiments that Mitrix is doing, Tom Edison is doing, where they are steadily increasing the dose given to these mice, and Tom intends to keep going until they see something serious happen. And there's a factor that they're at over 1% of the total mouse mitochondria per dose, with no ill effects at this point. But it's like TBD, but hopefully we'll have some data on that.
Well, so the nice thing on that, and Tom thankfully is doing that, we're going to have that data pretty soon, I hope by the next time that we get together. But it's a very doable study, right? Like literally, like we can do that study. Okay, final question, because I can't let my own talk put us behind on schedule. Okay, I can't do that, okay? Final question, go ahead.
So as you all know, my children have MELAS, and the S stands for stroke-like episodes. Brain, so when those macrophages got to the brain in 30 seconds, that caught my attention. And when you have a stroke-like episode, for a MELAS patient, the treatment is arginine, typically over 72 hours. I thought to myself, geez, maybe some mitochondrial transplantation would do the trick. So where are the chop people in this room? And I'd like to put that out there because this may be an example where it could cross over into the other side of the conversation, which is an urgent care, but ongoing care. Thank you.
Melanie, would you want to take that one on? Melanie Walker, who's actually given mitochondria to human beings for stroke.
I'm willing to try and I think anything that we are rigorously evaluating and that we're honest about what the risks and benefits are, and there's no. You also worry about secondary gain and all these shenanigans, but when you peel away all the stupidness and you can really think through, is there no benefit here and a very small risk? Yesterday I know you're short on time, yesterday I was thinking hard about the history of how we think about medicine when there's a downside or an unknown. And as what I do, an vascular neurosurgeon, we in the brain, we want to put stents in the brain. And when we first started thinking about putting hardware, and now we do brain and computer interfaces, right? We started thinking about putting hardware in the brain, and everybody's like, well, it costs clots because they're foreign bodies and it's awful. And half the community was like, well, you can't do that because you're going to get clots in the brain, and that's counterintuitive. And all of us were like, it's a known thing. So let's treat the clots. But you get to live if you have a stent, and your life gets a whole lot better. So tell me what I need to do to treat the clots. All my patients get dual antiplatelet. They get blood thinning medicine so they don't get clots, but they're willing to go through that badness, an awful side effect. And we didn't spend 10,000 million years saying, well, we can't do this because there's this side effect and it's bad. And we were just like, let's deal with it. And so I don't discount any of the bad things that could happen, and I don't think inflammation is crazy. I agree, everything is there. Let's name it and measure it and plan for it and do it. But unless we start doing it, we're going to be in an echo chamber of all the things that could happen, and all the things that couldn't happen, and all the things that were bad, and all the things that just do it. And what? Well, I don't think the glass is half full. I don't think it's half empty. I think it's refillable. Right? You just do it and you try, and then up and down, and I don't know, but you be honest and you be rigorous and you try. And as transparent as you can. So I'm willing to try. If there's a scientific rationale and we can be rigorous about it, then where I draw the line is where I'm certain that the risk is higher than the benefit. Like that, even if we feel like we need to do something because there's nothing, but if the risk threshold I know for certain is worse than any potential benefit, don't ask me to do it because I won't. But if you get a 51-50 and there's a chance, and we can work through the scientific rigor. I'll try.
There you go. You heard it from, I think, the world's expert. Thank you. All right. Thanks everybody for attention. We are going to move on to our next section.